Hi, in this video we're going to be talking about 12.6. This should be the last video on 12.6. We're going to finish up our discussion of other quadric surfaces. So, in the last video, we always had all three variables squared, and we always had a constant. So I told you we're going to look at what happens if you manipulate that. The first thing that could happen is you could get a cone. And cones are very important for, camera work. The theory of relativity uses a lot of cones, if you really get into it. Focus diagrams for cameras. X squared over A squared plus Y squared over B squared. Oh man. Minus Z squared over C squared equals 0. Okay, how do you tell if you have a cone? By now, if you watched the last video, you should be pretty confident saying what we're going to write in terms of a biography of this function. Okay, all three variables, that's given. If one was missing, it would be a cylinder. Okay, one negative variable. I don't have a nice mnemonic like we did with one sheet. If it was just one negative variable and we had a constant, hint, we would have a one-sheet hyperboloid. But now there's no constant, or the constant 0, however you want to think of it. And all power to 2. All power 2. We haven't looked at what happens if we start playing with the powers of 2. So it's directed along the negative variable, just like in the last video. It's the odd one out. We're going to set the negative guy equal to 0. Is not going to do anything. Not giving us anything, right? Picture if we covered that up. We'd have x squared plus y squared equals 0. That's only going to give us the origin. So sorry, it's maybe a little more accurate to say gives the origin. So it's not very helpful unless it helps you to understand that these cones are going to pass through the origin. So we're going to instead plug in values, key values for the negative to find the sketches. Traces. And the traces, if we cover this up, right, ignore the 0 also. What would that end up looking like? Circles or ellipses? Ellipses. Okay, and what I mean by key values, one more time, what do I mean by key values? We mean values that will divide nicely, values that will divide nicely. So, example. Someone gave me z squared minus 9x squared minus 4y squared equals 0. Okay, the first thing I want to say is there's no constant, and they're all squared. That's what makes it a cone. You want to be very careful here. Because the fact that we have one negative in our standard equation and the fact that we have two negatives here doesn't mean anything. Why? Because I can just multiply by a negative and it will have no effect on things, right? I'm allowed to move terms around, right? If we just move all these to the other side, it's just 0. There's no constant forcing the signs to happen. So, more important than this one, that is still true though, is the fact that we have no constant and they're all to the power of 2. That's what you want to focus on. So I have 9x squared plus 4y squared minus z squared equals 0. If that confuses you, right? What I'm saying is if I just multiplied by a negative, right, these have to be the same. Because a negative times 0 is still going to be 0. We're going to divide by the number I need to get all of the variables' coefficients to go away. So if I divide it by 9, that could work, but then we just have this ugly coefficient. So I'm going to divide by a nice number, so to speak. The lowest common multiple. I'm going to divide everybody by 36 on both sides. But the other side's always going to be a 0. And now we're going to have this old standard equation. And again, why does a negative 1 matter? Well, once you divide by a negative and make sure there's only one negative variable, we are still going to be directed along the negative variable. So I may have said earlier, I may have misspoken. It's not that the negative variable doesn't matter, but the fact that there's 2 negatives or 1 negative, that doesn't matter because we can just manipulate that by multiplying by a negative. Listen to me really clearly here. Get one negative variable. Okay. If you have some negative signs, get it so that there's one negative variable. That negative variable is going to be our direction. Now, in terms of picking out nice numbers, we want numbers that'll divide nicely. Numbers that'll divide nicely for that negative variable. So what will get divided nicely? Can you think of it? Z equals 6 plus or minus 6. We'd get x squared over 4 plus y squared over 9 minus 36, whether it was positive or negative, over 36. So we'd have x squared over 4 plus y squared over 9 equals 1. And what does that look like? It looks like an ellipse. We're directed along the negative variable. In this case, we are talking about z. So I'm thinking about directing it up and down along the z-axis. We'll go through the origin. And now I'm just going to go up to a height of 1, 2, 3. I'm going to shrink that. 1, 2, 3, 4, 5, 6. Along the positive x, z, and the negative z. And while we're there, what are we going to do? We're going to sketch lines parallel to the x and y. And we're going to find the intercepts. So for this kind of for this kind of ellipse, where would the intercepts be? The x's should be 2. And the y should be 3. And then the same thing down here. And what we want to do is sort of draw our sketch lines going through the focal point. That's why a lens diagram is really a nice analogy if you've ever seen a lens diagram. We're talking about a cone. Unlike some of the cones you might have seen in your previous life, this has an upside and a downside to it. We're actually going to study that a lot in this class. It's going to be like a positive branch and a negative branch situation. Okay, so that's what we're talking about with a cone. We're talking about kind of a positive side of the cone and a negative side of the cone. Next. So now we've exhausted all the options for having all 3 squared. So the next 2 we're going to talk about is what happens if they're not all 3 squared. So paraboloid, my favorite guy. I like saying it. I like how it's spelled. A paraboloid. The standard form here is x squared over a squared plus y squared over b squared equals c times z. Maybe some coefficient times the z variable. The first thing that should jump out at you is like, whoa, 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 whoa. I thought we were only going to talk about over c squared, stuff like that. No. So what's going on here? It has all three variables. Remember, if it didn't have all three variables, we'd be talking about a cylinder. But only two are squared. And then here's the key. Both squares are positive. I've been writing it like this. Okay. Opens along axis of the linear variable. And what do I mean by linear? I mean power 1. So in that standard form right there, it'd be the z. But does it have to be z? No. Could be anybody. The coefficient of the linear variable tells us open in the positive direction or negative direction. Why didn't I just say open up or down? Well, I think you've noticed there's lots of problems with up or down. Without spoiling anything too much, the three paraboloids we're going to talk about are paraboloids that look like they could open in the x direction, they could open in the y direction, or they could open in the z direction. Picture pills. Like half of a capsule, I guess. All right? And we don't know which one's up. Like, up will just mean in the positive direction. I guess up was the z. I guess that's what my mind wants to say. Well, no, obviously up is the z. But I'm saying we could open in the positive y or the positive x as well. Just be careful about that. All right. Let's do an example. Maybe I'm getting bogged down here. Maybe you guys aren't as confused about why we have to be more careful with the up and down language now. X squared plus 4y squared minus 4. Whoa, whoa, whoa. No one told me there'd be a constant. Okay, I didn't say anything about there not being a constant. I also want to just take this opportunity to talk about what that negative 4 is going to do. This is just a shift, okay? This is a shift. How can I tell which way we're shifting? We're going to move it over to the other variable. That's how. But first, do we see why this is a paraboloid? We have x squared, we have a y squared, we have a z. But the z is not being squared. There's a constant, but we can just move it to the other side and say z plus 4 equals x squared plus 4y squared. Z equals 0 is going to give us a trace in the xy plane. I forgot to write that down over the notes. So set linear variable equal to 0 for a trace in the coordinate plane, in a coordinate plane. A coordinate plane. One of them. There's 3. Sorry, I got so obsessed with drawing them. That's one thing I feel good at drawing, and you're probably laughing at me because maybe you thought my drawings were sad. I don't know. I feel pretty good about it. If z equals 0, I'd have 4 equals x squared plus 4y squared. I'm not sure how you feel, but right now I feel like I've done enough of these for a lifetime. Do you know what that looks like? What would you do next? Well, you have x and y. I think we should divide by 4, maybe. That's what I'm saying. I'm just getting tired of doing ellipses, you know? That's an ellipse. Can you draw it? Can you draw it? We're going to draw it in the 3D space. We're directed along the z-axis. Are we opening up or down? Are we opening toward the positive z or the negative z? How do I tell? We're opening along the axis of the linear variable, and then the coefficient is going to tell me to open in the positive direction or the negative direction. So what's the coefficient of that group? That coefficient is positive. So we're going to open in the positive z direction. We're opening up. If there were a negative here, we'd open down. Okay? And toward the negative z-axis. Now I'm saying up or down. So I want 2 in the x direction, 1 in the y direction, and this will give me a trace. And that right here is a shift. What do we think? In the z direction, in the positive z direction, or the negative z direction? Well, when it's +4 in a group like that, this is shift down 4 in the z direction. So we're talking about 1, 2, 3, 4. You could find that by setting the other two variables equal to 0. Right? If x and y were both 0, you'd have z equals -4. And now what we're going to draw is my paraboloid. And it goes infinitely up. I want to be clear about that, I guess. It keeps going. But those make it look uglier, right? Maybe I need to trim them? I don't know. Okay, but it goes infinitely up. If I was drawing this freehand, I would have drawn something like this. So these could also be called elliptic paraboloids. Why am I emphasizing that now? Well, the cross sections here are ellipses. What else could we talk about, though? Well, the cross sections could happen to be hyperbolic. Now, this one will always specify hyperbolic. If we say paraboloid, we mean nice paraboloid. These hyperbolic paraboloids, I'll probably be drawing it for like 15 minutes before I end up having one nice enough for the video. A hyperbolic paraboloid will have the form x squared over a squared minus y squared over b squared equals a constant times z. 3 variables. Again, if there's 2, it'd be a cylinder. Only 2 of them are squared, though. One of the squares, this is what matters, one of the squares is negative. Could the z be negative? Yeah, it just means it's opening in the opposite direction. Okay. The degree 1 variable, the linear variable, gives direction. We're directed along the linear variable. Again, the odd one out. Plug in. Make sure you plug in positive numbers and negative numbers to the linear variable. For the traces. It has a serious effect on things. We're just going to spend the rest of the video doing our actual example, but just so you can see what serious effect I mean. So, simple. X squared minus y squared minus z equals 0. Why is this not a cylinder? Can you tell me right now why it's not a cylinder? Make sure. It's because there's 3 variables here. We have all 3 variables. How many squares do you have? You only have 2 of them squared. That means it's going to be a paraboloid. It's going to be a paraboloid, whether it's hyperbolic or elliptic. Okay, one of those 2. I'm going to rearrange in the standard form. x squared minus y squared equals z. So it's a hyperbolic paraboloid along the z-axis. The z is linear. When I say we need to just make sure we're doing both positives and negatives, here's why. This would be x squared minus y squared equals 1. That is a hyperbola. But there's funky things happening with x's and y's. This is a hyperbola where if we had x equals 0, there'd be a problem. So this is a hyperbola that opens up like this. When the y equals 0, we'd have x equals plus or minus 1. And at some point in your life, you learned how to draw nicer looking ones than me. Talking about this kind of shape, everybody. And it's both of them. These are not functions. And likewise, if z equals -1, we'd have x squared minus y squared equals -1. And at first you might be like, well, why does it affect anything? We need this number to be 1. So that's negative x squared plus y squared equals 1. So now it doesn't make sense for the y to be 0. So now we're talking about hyperbolas that open like that. And that tension of what happens above the xy plane when z's are positive, above the xy plane, we want to look like this. When z's are positive, I want to look like that. When z's are negative, I want to look like this. And that cough, cough, sharp turn is what's going to make us have a weird shape and have a tension. So I'm just going to try to draw it freehand for you. And you can look at the GeoGebra video and see the cross sections. I'll draw the cross sections on this potato chip type graph after I draw it. Why do I call it potato chip? Because it's going to end up looking like a Pringle. So I want you to visualize a Pringle while I draw this. It's also known as a saddle. Okay, so it's a saddle. It's a saddle graph or a Pringle graph or whatever you want to call it that helps you understand what's going on here. So this black stuff was working around here. There's like a 3D shape of the hyperbola going in that direction. And then the curvature down here is going in and going in. I don't like how this art looked. Oh no. I think more like this. Yeah, something like that. Obviously it goes on forever that way. Okay. I'm not trying to say it's limited. Saddle is another key term for this. We also have, because there's this kind of curvature too, and this kind of curvature sloping along. So it's a really important type of surface, but it's a really funky type of surface. And that's quite frankly the best I'm going to do about this. I may or may not have tried for a while, and you're just seeing the final draft. I encourage you to watch the GeoGebra video to get a better sense of the 3D geometry. I encourage you to play around with GeoGebra. Again, I'm not going to judge your pictures. What do I want you to know after watching the hour-long 12-6 video? What do I want you to know? I want you to understand what the shape will look like, why we care, why do we care about surfaces, because that's the rest of the course on some very basic level. We're either going to walk along these surfaces or we're going to find the volumes of them or their derivatives, the slopes, all that sort of stuff. So you shouldn't be shocked for the rest of the year when you see the word paraboloid. And I'm talking about the nice paraboloids. All right, I hope you understood some of it. Again, please watch the GeoGebra one if that makes sense to you. If this didn't make sense to you, I guess. All right, thank you for watching. Bye.